In the wide outer region of the solar system where sunlight arrives as a faint and weakened glow, Comet Leonard moves through a space defined by low temperatures, scattered dust and the distant pull of the sun that still holds it in a long and stable orbit. The environment around the comet in this region remains calm, with few objects nearby, and long stretches between any fragments of rock or ice that drift quietly along their own paths. Leonard travels through this broad expanse at a pace governed by its orbit, which carries it far beyond the planets into a zone where the sun appears only as a bright point against a dark background. The light that does reach the comet is not strong enough to warm its surface significantly. Instead, Leonard remains cold, with its outer layers preserved in a frozen state that reflects the long history of its distant origin. The cold temperatures maintain the stability of ices composed of water, carbon dioxide, and other volatile substances that form much of the comet's nucleus. These ices remain solid because the faint sunlight in this outer region cannot heat them enough to change their state. The nucleus itself stays dark, absorbing much of the light that reaches it. This darkness results from the presence of dust particles and carbon-rich material that coat the comet's surface, creating a layer that protects the underlying ice. As Leonard moves through this region, it experiences almost no activity. The low temperatures keep its surface quiet, with no gas escaping and no visible coma surrounding the nucleus. The space around the comet remains clear with no dust trails or jets. The nucleus travels as a compact object, its structure unchanged by the weak sunlight. The outer solar system at this distance contains little more than scattered dust grains and the occasional small body, all bound by the gravity of the sun. Leonard's motion through this region follows predictable paths, determined by the balance of gravitational forces acting upon it. Although the sun dominates these forces, distant stars and large planets can exert minor influences over long periods. These influences slightly adjust the comet's orbit, but the changes remain small within the timescale of a single passage. In this quiet zone, the comet experiences only faint traces of the solar wind, a stream of charged particles flowing outward from the sun. These particles travel in all directions, but their density remains low at this distance, and they have little effect on the comet's surface. The outer atmosphere of the solar system, known as the heliosphere, extends to great distances, shaping the region through which Leonard moves. The solar wind slows as it travels outward, and its interaction with interstellar space creates a boundary that influences how particles move. Leonard travels well within this boundary, though far enough from the sun that conditions remain gentle and cold. The comet's orbit brings it slowly inward from this distant region. The amount of sunlight increases gradually as Leonard moves closer to the sun, but in the outermost region, the increase is too slight to cause any visible change. The nucleus remains quiet. The dust on its surface stays undisturbed. The ices remain stable and unaltered. The environment offers no strong forces or collisions that would modify the surface. The outer region through which Leonard travels contains remnants of early solar system formation. Many of the dust grains present here formed billions of years ago. These grains drift in long orbits, rarely encountering other objects. Leonard's nucleus contains some of the same materials that populate this distant region. The surface of the comet bears signs of its ancient history, including fine dust, dark coatings, and fractures produced over long intervals by the passage of time. The outer solar system is characterized by slow processes. Changes in temperature occur gradually, and the motion of objects unfolds at a steady pace. Leonard's orbit through this region can last millions of years before it reaches the inner parts of the solar system. During most of this time, the nucleus remains unchanged. It retains the structure and composition it acquired long ago when icy fragments gathered into the body that now forms the core of the comet. The light from the sun in this distant region is not sufficient to create shadows that shift quickly across the surface. Instead, the few shadows that form remain static and faint, moving only as the comet slowly rotates. This rotation allows the nucleus to experience slight temperature variations from one side to the other, but the differences remain too small to produce any activity. The nucleus remains dark and stable, with its surface cold enough to keep all volatile materials frozen in place. The outer region also contains gravitational influences from the giant planets, though at this distance the effects are minimal. Over long intervals, these influences can alter the path slightly, guiding the comet inward or outward, depending on its position relative to the planets. Leonard's path carries it gradually toward regions where these influences become stronger, but in this outer portion, the motion remains quiet and uniform. As Leonard continues its inward travel, the balance of forces acting on it changes slowly. The Sun's gravitational pull strengthens, drawing the comet closer along its elongated orbit. The faint sunlight begins to warm the outer layers of the nucleus by a small amount, but the warming remains insufficient to cause the ices to sublimate. The comet still travels as a quiet, compact object with no visible cloud surrounding it. The environment transitions gradually, with no abrupt boundary marking the change from distant cold to regions where the sun exerts a stronger influence. Leonard's passage through this outer zone marks the earlier stage of its journey toward regions where it will eventually become more active. Yet the outermost region remains defined by quiet conditions that preserve the nucleus and protect its ancient materials from alteration. This part of the journey reflects the slow and steady nature of cometary motion, through space shaped primarily by gravity and by the faint light of the sun. Comet Leonard continues along its long orbital path, carrying its frozen structure inward, with no visible signs of change sustained by the cold environment that defines the outer region of the solar system. Comet Leonard continues its long inward sweep along an orbit shaped by gravity and time, moving through a path that stretches across a vast portion of the solar system. This orbit forms a long ellipse, carrying the comet from the cold outer regions toward the warmer zones nearer the sun. As Leonard follows this path, its speed changes gradually. When it travels far from the sun, the gravitational pull is weaker, causing the comet to move more slowly. As it draws nearer to the inner regions, the stronger gravitational field increases its speed. This steady change follows the same principles that guide the orbits of planets and other small bodies, creating a predictable motion that unfolds across many thousands of years. The orbit of Comet Leonard begins in a region where the sun appears small and distant, and the comet remains preserved in a frozen state. As it starts its inward journey, the conditions around it change only gradually at first. The increasing sunlight remains too weak to warm the nucleus significantly, and no visible activity develops. Leonard moves quietly, carrying its nucleus and the ancient material inside it toward regions where the sunlight will eventually become strong enough to affect its surface. The shape of the orbit reflects influences from many sources. Gravitational interactions with distant stars may have nudged the comet onto its present path long ago. These interactions occur when passing stars disturb the outermost reservoir of icy bodies, sending some of them inward. The long duration of these processes means that no single event shapes the orbit alone. Instead, the orbit develops through the accumulation of many small influences that act across long intervals. Now, as Leonard approaches the inner solar system, its orbit carries it through regions where the gravitational pull of the giant planets becomes more noticeable. When the comet travels near the orbital paths of these planets, their gravity can adjust the motion slightly, altering the tilt or shape of the orbit. These adjustments remain gentle, but over thousands of years they contribute to the final path the comet follows. The orbit of Comet Leonard is long enough that the comet spends most of its time far from the sun. Only a small part of its journey occurs in the inner region, where sunlight creates visible activity. The rest of the time, the comet remains quiet and cold, travelling through space without forming a coma or tails. Leonard's current inward motion marks one of the rare periods when it enters a region where its appearance will change. As Leonard moves closer to the sun, its speed increases. The change in velocity remains smooth and gradual. The comet follows the curve of its orbit without deviation, guided by the gravitational pull that maintains its motion. The increasing sunlight begins to warm the outermost layers of the nucleus, but does not yet cause significant outgassing. The dark surface absorbs light slowly, and the cold interior remains well insulated. In this region, Comet Leonard begins to transition from a completely inert object into one that will soon display the first signs of activity. The orbit brings Leonard into sections of the solar system populated by small bodies, though the distances between them remain large. The comet encounters no collisions and experiences no strong external forces besides gravity. The motion continues smoothly. Because the comet's orbit is long, its inclination and orientation in space matter. The tilt of the orbit determines how Leonard approaches the Sun, whether it passes above or below the orbital plane of the planets, and how sunlight reaches different parts of the nucleus. This orientation also affects how observers on Earth will view the comet. As the comet continues inward, the sunlight that reaches the surface increases in strength, warming the outer layers enough to begin altering the physical state of the ices. Sublimation. The process where a solid turned directly into a gas begins slowly in the regions that receive the most sunlight. These early changes remain faint and limited to small areas. The warmed material may begin to loosen the dust coating the surface, though no large-scale features emerge yet. The orbit continues to shape the pace of change. Leonard travels along a path that brings it steadily closer to the Sun. Each day of inward motion increases the sunlight and the potential for more vigorous activity. At this stage, the orbit dominates the behaviour of the comet. The shape and speed define how quickly the temperature changes across the nucleus. When the comet approaches the region where the giant planets exert their strongest influence, the gravitational interactions can adjust the orientation of the orbit slightly. These changes may affect the points where Leonard crosses the orbital plane or the distance at which it approaches the Sun. Such adjustments shape the geometry of sunlight on the nucleus, influencing how and when the surface begins to sublimate. The comet's rotation also plays a role in how the orbit affects the nucleus. As Leonard rotates, different regions of the surface receive sunlight. Some areas become warm enough to sublimate ices before others. This rotation interacts with the orbital geometry to create patterns of heating that shift as the comet moves closer to the Sun. The combination of rotation and orbital position shapes the first areas of outgassing that will appear as the comet continues its inward journey. As Leonard travels along the inward arc of its orbit, the path becomes narrower and the gravitational pull of the Sun becomes more pronounced. The motion grows faster and the pace of thermal change increases. The surface begins to exhibit small variations in temperature that indicate the early stages of activity. However, these changes remain subtle and slow-moving at this distance. Sublimation does not yet produce a visible coma or tails. The orbit, wide and elongated, remains the dominant factor shaping the trajectory. Leonard passes through regions where the influence of the solar wind becomes slightly stronger. The solar wind, composed of charged particles emitted by the Sun, flows outward through space, and its density increases gradually as the comet approaches the inner regions. Although the effect remains small at this stage, it begins to contribute to the forces acting on the comet's surface, especially in regions where the earliest traces of outgassing will emerge. The geometry of the orbit also determines how long the comet remains in regions where sunlight can influence its structure. As the comet moves inward, the speed of its travel increases, shortening the time spent near perihelion, the closest point to the Sun. This brief passage through the warmest region of its orbit will shape the extent of the activity Leonard experiences. Before reaching that point, the orbit continues to guide the gradual warming of the nucleus. The increasing sunlight begins to penetrate slightly deeper into the surface, affecting the layers just beneath the dust coating. This change represents the earliest internal response to the approaching Sun. These layers remain solid with no visible outflow of gas or dust. Yet the thermal gradient begins to shift. At this stage in its orbit, Comet Leonard transitions from a distant frozen object to one moving toward an environment where sunlight will become strong enough to reshape its appearance. The orbit sets the pace and direction of this change, guiding the comet toward regions where the next stages of activity will develop. The comet continues steadily carrying its frozen nucleus along a path determined by forces that act across long intervals of time, unaffected by anything except the gravitational pull that defines its journey toward the inner solar system. The earliest origin of Comet Leonard can be traced to the remote region known as the Oort Cloud, a vast spherical distribution of icy bodies that extends far beyond the outermost planets and marks the distant boundary of the Sun's gravitational reach. In this region, the Sun appears no brighter than a nearby star, and the temperatures remain low enough to preserve ices for billions of years. Leonard forms from material that collected in the early stages of solar system development when small icy bodies merged gently within the cold outer reaches of the protoplanetary disk. These icy fragments contain water, ice carbon dioxide ice, and more volatile ices such as carbon monoxide, along with dust grains and the earliest mineral particles that condensed as the disk cooled. These components gather into small aggregates that later become the nucleus of the comet. In the Oort Cloud, these small bodies remain largely unchanged, protected from significant heating or collisions by the immense distance that separates them. The cloud contains countless icy fragments, each following a slow orbit influenced by the Sun but also by the gravitational effects of passing stars and the tidal forces of the Milky Way. Over long intervals, these external forces can disturb the orbits of comets, nudging some of them inward. Leonard is one such body whose orbit shifted slightly due to the influence of distant stars setting it on a long trajectory that brings it back toward the Sun after many thousands of years away. The Oort Cloud serves as a reservoir of long-period comets' bodies that take many millennia to complete a single orbit. Leonard's earliest material remains preserved in this environment, where the lack of significant heat or radiation protects the ices from sublimation. The body that becomes Comet Leonard likely formed closer to the Sun during the early stages of solar system formation. After its formation, gravitational interactions, possibly involving the giant planets, scattered it outward into the distant Oort Cloud. Once there, Leonard settled into a stable orbit, remaining in deep, cold conditions for a long span of time. This environment allowed the comet to retain materials from the early solar system with minimal alteration. The composition of Leonard's nucleus reflects the mixture of ices and dust that formed in the protoplanetary disk. Dust grains within the nucleus represent some of the earliest solid materials to form around the young Sun. These grains carry records of temperature, pressure, and chemical composition present during the early stages of planetary formation. The ices encasing them preserve volatile compounds that remained frozen in the cold outer regions. The structure of the nucleus reflects the gentle aggregation of ice and dust in the early disk. Unlike larger bodies that underwent internal heating, the icy aggregates forming, Leonard remained cold, allowing fragile materials to survive and become part of the comet's long-term structure. The Oort Cloud itself forms after the planets have accumulated most of their mass. During the late stages of planet formation, gravitational interactions cause a large population of icy bodies to scatter outward. Some of these bodies settle in orbits that take them far from the Sun, eventually forming the Oort Cloud. Leonard belongs to this population. When the comet eventually returns toward the inner solar system, it carries material that formed billions of years ago, preserved by the cold environment. In the Oort Cloud, time passes without significantly altering the nucleus. The ices remain solid. The dust coatings remain undisturbed. No sunlight reaches the interior layers, leaving them as pristine as the day they formed. The gravitational pull of the Sun remains weak at this distance, and the comet moves slowly through this environment. The gradual influence of the Milky Way's tidal forces subtly adjusts the comet's orbital path, but these changes are small across the lifespan of a single orbit. The Oort Cloud is not a uniform environment. Its outer regions experience stronger gravitational effects from passing stars, while its inner regions remain more stable. Leonard may originate in one of the intersections where objects remain bound more tightly to the Sun. Over time, gravitational interactions from distant stars may push the comet into a new orbit that carries it outward and inward along a long elliptical path. Once the orbit shifts inward, Leonard begins the long descent toward regions where sunlight becomes strong enough to influence the structure of the nucleus. The journey from the Oort Cloud to the inner solar system takes many thousands of years. During most of that time, Comet Leonard moves through regions where external forces remain too weak to cause visible change. Only when the comet approaches the outer planets does sunlight begin to affect the surface. But the earliest origins remain locked in the Oort Cloud. where icy bodies like Leonard retain material from the early solar system. The structure of the comet reflects this origin. The nucleus consists of loosely bound ices and dust that formed without strong compaction. The low density of the nucleus indicates that voids remain within the structure, a feature that results from the gentle nature of the aggregation process. The dust grains embedded in the ice represent the earliest generation of solids, some of which may include mineral fragments formed in earlier stars. The Oort Cloud preserves these materials without significant modification. Over long intervals, the comet's orbit may shift due to gravitational influences that accumulate gradually. Each passing star can alter the velocity or direction of the comet slightly. Over many such encounters, the cumulative effect can place the comet on a path that brings it back toward the Sun. Leonard's present orbit reflects this slow and complex history. Its return to the inner solar system carries the remnants of the early protoplanetary disk, preserved within an icy matrix that has remained stable for billions of years. As Leonard leaves the Oort Cloud and moves into regions where sunlight becomes marginally stronger, the compositional properties of the nucleus begin to matter more. The dark surface helps absorb sunlight when the comet approaches the inner regions. The mixture of ice and dust responds to warming by slowly loosening the structure, leading to changes that will manifest as activity once the comet nears the Sun. But these changes remain absent in the Oort Cloud. There the nucleus remains in a state of near-perfect preservation, with no outgassing and no coma. The Oort Cloud marks the starting point of Leonard's long journey. The materials forming the nucleus carry the record of early solar system chemistry. Each grain reflects conditions that gradually shape the disk from which the planets formed. The ice within the nucleus locks these grains in place, preserving them through the cold and distant environment of the outermost solar system. When the comet eventually enters warmer regions, these materials will become accessible, but their earliest origin remains in the Oort Cloud. As Leonard travels inward, it brings with it the chemical and structural record of its formation. The nucleus that developed in the early disk and remained preserved in the Oort Cloud now approaches regions where sunlight will begin to reshape its outer layers. But the earliest origins remain tied to the cold outer reaches where the comet assembled its structure billions of years ago, and where it remained until gravitational influences slowly guided it toward the inner solar system. After its long preservation in the distant Oort Cloud comet, Leonard begins the slow inward drift that unfolds across many thousands of years, driven by subtle gravitational influences that accumulate gradually. This drift does not begin with a sudden shift, but instead with small adjustments to the comet's orbit caused by the gravitational pull of passing stars. When stars move through the neighbourhood of the Oort Cloud, their gravity can alter the orbits of the icy bodies within it. Even a slight change in direction or speed can place a comet on a new path guiding it inward toward the Sun. Leonard experiences such influences over long intervals, allowing its orbit to evolve from a distant stable trajectory into one that carries it slowly toward the inner parts of the solar system. The gravitational field of the Milky Way also plays a role. The tidal forces acting across the Oort Cloud exert gentle pressure on the orbits of its objects, causing their shapes and orientations to shift slowly. These forces create long-term changes that influence the overall distribution of comets in the cloud. Leonard's orbit changes gradually under the combined effect of these forces, moving it from a distant cold region into an elongated path that stretches inward. As the comet begins its inward journey, the pace remains slow. The vast distance between the Oort Cloud and the inner solar system means that the comet travels for many thousands of years before reaching regions where sunlight becomes strong enough to cause noticeable changes. During this long inward drift, Leonard remains preserved in its frozen state. The ices that form the nucleus remain solid. The dust layers that coat the surface remain undisturbed. No activity develops because the sunlight remains too weak to warm the surface significantly. The motion continues quietly through regions where the density of material is low and collisions remain rare. As Leonard approaches the outermost sections of the solar system, the gravitational influence of the Sun becomes slightly stronger, guiding the comet more directly along its inward trajectory. The temperature in these regions remains extremely low, sufficient to keep the comet inert. The sunlight grows stronger at a slow pace, creating a gradual increase in the temperature of the outer layers. These changes mark the early stages of the comet's transition from a static object into one that will eventually develop a coma and tails. The rotation of the nucleus interacts with this increasing sunlight. As Leonard rotates, sunlight reaches different regions of the surface, creating temperature variations from one side to the other. These differences remain small at this stage, but represent the beginning of the thermal changes that will shape the structure of the comet as it moves inward. The gravitational influence of the giant planets begins to matter as Leonard approaches their orbital regions. The path of the comet may shift slightly when it comes into the region, influenced by the gravity of Jupiter or Saturn. These changes can adjust the orientation or tilt of the orbit, shaping how Leonard will approach the inner solar system. The giant planets also influence the timing of the orbit, guiding the comet along a path that eventually brings it within reach of the sun's stronger radiation. The inward drift continues as Leonard crosses regions where the density of the solar wind increases slowly. The solar wind consists of charged particles emitted by the sun. At great distances, these particles exert little influence on the comet, but as Leonard moves inward, the density of the solar wind becomes slightly higher. The particles interact weakly with the nucleus, though these interactions remain too faint to cause any visible change at this distance. At this stage in its journey, Comet Leonard remains fully intact with its nucleus unchanged by external forces. The long inward drift still keeps the comet in regions where sunlight remains too weak to cause sublimation. The temperatures do not rise enough to alter the state of the ices within the nucleus. The preserved materials remain unaltered as the comet continues its gradual inward motion. The comet's orbit stretches across regions that contain relics of early solar system formation, including dust grains, small icy fragments, and scattered rocky objects. Leonard moves through these regions without noticeable interaction. The distances between objects remain large enough to prevent collisions. The flow of the solar wind does not disturb the nucleus significantly. The gravitational field continues to guide the comet's path in a smooth and predictable manner. As Leonard moves farther inward, the sun's gravitational pull grows stronger. This change influences both the speed and trajectory of the comet, causing it to move more quickly along its elliptical path. The increase in speed reflects the conservation of energy in orbital motion. When the comet falls toward the sun, it accelerates. When it moves away, it slows. At this stage, Leonard remains on the inward portion of its orbit, gathering speed as it approaches regions where sunlight will eventually influence its structure. The gradual inward drift shapes the thermal environment of the nucleus. The slight increase in sunlight begins to penetrate the outermost layers. The dust coating absorbs this light, warming slowly. The deeper layers remain insulated, but the outer layers begin to exhibit subtle changes. The warming does not yet produce gas flow, but the temperature gradient between the surface and the interior begins to shift. These changes remain the earliest signs of the transition to activity. The inward drift also affects how the comet interacts with the gravitational fields of the planets. As Leonard approaches the region beyond the giant planets, the gravitational influence of Jupiter becomes one of the strongest external forces acting on it. Jupiter's gravity can alter the orbit's shape, potentially changing the path enough to influence how close the comet will approach the Sun. These gravitational encounters remain gentle but significant over the timescale of the orbit. The rotation of the comet's nucleus continues to affect how sunlight influences the surface. As Leonard rotates, sunlight warms different sides of the nucleus during each rotation. The rotation period determines how long any region remains exposed to sunlight. At this distance, the warming remains insufficient to cause sublimation, but it represents the earlier stage of the thermal cycle that will become more important as the comet continues inward. The inward drift marks the beginning of the comet's transition into a region where it will eventually become active. The changes remain slow and subtle at this stage. The nucleus stays dark and stable. The ices remain frozen. the dust layer remains intact. Yet the gradual increase in sunlight begins to alter the temperature profile of the surface, preparing the comet for the next phase of its journey. Leonard's inward motion reflects the balance of gravitational forces acting upon it. The slight nudges from distant stars and the tidal influence of the galaxy start the journey. The gravity of the Sun then guides the comet along its elongated orbit, drawing it inward. The comet follows this path without interruption, moving from the distant cold of the Oort Cloud toward regions where sunlight will play a more significant role in shaping its behaviour. The long inward drift remains a quiet phase in the comet's journey, dominated by slow changes and low temperatures. As Leonard moves closer to the Sun, the pace of change will increase, leading to the first visible signs of activity as the comet approaches the outer planets and enters regions where sunlight becomes strong enough to warm the frozen nucleus more significantly. As Comet Leonard approaches the region influenced by the outer planets, the gradual increase in sunlight begins to produce early signs of change across the surface of its frozen nucleus. The outer planets occupy a large portion of the solar system, and their combined gravitational fields create a complex environment through which the comet now travels. Although the distance between Leonard and any single planet remains large, the gravitational influence becomes stronger than it was in the distant regions of the Oort Cloud. This influence helps refine the comet's orbital path, adjusting its trajectory as it moves inward. The environment around the outer planets contains the first noticeable increase in solar radiation compared with the faint light that reaches the Oort Cloud. The sunlight in this region remains weak relative to the inner solar system, yet it provides enough warmth to begin altering the surface of the comet. The dust coating that covers Leonard's nucleus absorbs light and warms slowly. Beneath this dust layer lies a mixture of frozen water, carbon dioxide, and other volatile ices that formed during the early stages of solar system formation. As Leonard travels through this region, the temperature increase remains modest, but the warming begins to influence the behaviour of the outer layers of the nucleus. The dark dust on the surface absorbs sunlight more efficiently than the icy material beneath it. This creates a temperature gradient between the surface and the interior. The warmed surface layers do not yet initiate widespread sublimation, but the earliest signs of volatile release begin to appear in isolated regions where the surface absorbs more heat. Small pockets of gas may start to form beneath the dust layer, slowly loosening the structure. These early changes remain invisible because the gas does not escape in sufficient quantities to form a coma. Instead, the gas remains trapped under the dust or escapes in amounts too small to produce visible activity. Leonard continues to rotate as it moves inward. The rotation allows sunlight to warm different surfaces of the nucleus in a steady repeating pattern. Some regions of the nucleus experience longer periods of sunlight due to the orientation of the comet's rotation axis. These regions may warm slightly more than others, initiating early stages of sublimation in localized patches. The warming remains insufficient to create jets or visible outflows, but the temperature variations begin to shape the surface's response to sunlight. The gravitational fields of the outer planets influence Leonard's motion primarily by shaping the orbit's direction and orientation. As the comet approaches the region near Jupiter, the gravity of this massive planet begins to adjust the path more significantly. These adjustments occur over a long distance, gently altering the tilt or eccentricity of the orbit. The gravitational interaction does not affect the structure of the nucleus directly, but it determines how Leonard continues its inward motion and how closely it will approach the Sun. The region near the outer planets also contains a diffuse population of dust and small particles that move within the gravitational influence of these giant bodies. Leonard passes through this environment without significant collisions. The sparse distribution of material means that the nucleus remains undisturbed. The main influence in this region comes from the increasing sunlight and the long-range gravitational forces that shape the orbit. The sunlight becomes stronger as Leonard moves closer to the inner regions. The early heating begins to loosen the dust that coats the surface. In some areas, dust particles may move slightly as the underlying ice warms and changes structure. These movements remain small and do not produce visible changes, yet they indicate that the comet's journey toward activity has begun. In this transitional region, the structure of the nucleus becomes more responsive to thermal processes. The surface layers warm unevenly due to variations in dust thickness composition and surface features. Some areas absorb more light than others, creating different rates of warming. The rotation of the comet brings these areas into and out of sunlight in a repeating cycle. Each rotation contributes to the gradual warming of the outer layers. The warming of the ices beneath the dust layer begins to generate small amounts of gas as the sublimation process begins. Sublimation occurs when a solid turns directly into a gas without becoming a liquid. In comets, this process begins when sunlight warms the ices enough to release gas molecules. At this stage, the sublimation remains weak and does not create a visible coma. The gas may seep through cracks in the dust layer or escape in small quantities, leaving no observable trace at a distance. The gas that escapes may carry small dust particles with it, although the amounts remain too small to detect. These early dust movements may shift a loose material on the surface, altering the distribution of grains at a microscopic level. The nucleus remains mostly unchanged, but the earlier stages of cometary activity have begun. The gravitational influence of the outer planets plays an important role in shaping Leonard's path toward the inner solar system. Jupiter in particular exerts a strong gravitational pull. As Leonard approaches the region near Jupiter's orbit, the planet's gravity may adjust the comet's trajectory slightly. These adjustments can alter the distance at which the comet will pass the Sun, influencing the intensity of the activity that will develop later. The interaction remains gentle and steady, occurring over a long distance. The solar wind also begins to influence the comet more noticeably in this region. The density of the solar wind increases as Leonard moves closer to the Sun. Although the effect remains small compared with the inner regions, the solar wind begins to interact with the earliest pockets of gas escaping from the nucleus. This interaction does not yet form an ion tail, but it begins to shape the environment around the comet's outer layers. As Leonard continues through the region near the outer planets, the gradual warming continues to increase. The structure of the nucleus responds by loosening in places where the dust coating thins, or where sunlight reaches deeper layers. These subtle changes represent the earlier stages of activity that will eventually become visible as the comet approaches the inner solar system. The inward motion continues to accelerate as the gravitational pull of the Sun becomes stronger. The comet's speed increases and the pace of thermal change quickens. The sunlight warms the surface more effectively at this distance, and the rate of sublimation increases slightly. Still, the sublimation remains limited to localized regions and does not yet produce a visible coma. Leonard remains an inert object to a distant observer, but the internal processes shaping the transition toward activity have begun to strengthen. The region near the outer planets marks a turning point in the comet's journey. The nucleus preserved for billions of years in the cold environment of the Oort Cloud now begins to respond to the increasing sunlight. The gradual warming marks the beginning of the visible transformation that will occur later. These early changes provide the foundation for the larger-scale activity that will develop when Leonard moves into regions where sunlight becomes strong enough to release gas and dust in significant amounts. The earliest signs of activity deepen as Leonard approaches the next stage of its inward journey, preparing for the formation of the coma and the beginning of the outward flow of gas and dust that will eventually surround the nucleus. As Comet Leonard continues its inward path and the sunlight strengthens steadily, the structure of its nucleus becomes increasingly important in determining how the comet responds to the warming environment. The nucleus consists of a mixture of frozen water, frozen carbon dioxide, frozen carbon monoxide, and other volatile ices interspersed with dust grains that formed in the early solar system. These materials accumulated gently during the early stages of the protoplanetary disk, creating a loosely bound structure that contains both solid layers and regions filled with microscopic pores. The dust grains embedded within the ice include silicates, carbon-rich compounds, and mineral fragments that condensed from the cooling disk long before the planets formed. As Leonard moves closer to the Sun, the dark dust on the surface absorbs sunlight more efficiently than the underlying ice. This absorption increases the temperature of the outermost layers, forming the thermal gradient that drives sublimation. The dust layer acts as a porous blanket over the ice, slowing the loss of heat and delaying the onset of vigorous activity. This layer varies in thickness across the surface, with some regions covered by fine grains and others by coarser material. These variations influence how sunlight reaches the ice beneath. In areas where the dust layer is thin, sunlight penetrates more easily and warms the ice, initiating localized sublimation. In regions with thicker dust coverage, the sunlight warms the dust more slowly, delaying the sublimation process. While the sunlight remains too weak in this region to produce large jets or a visible coma, it begins to influence the internal structure of the outer layers. The warming causes the ice to change phase, slowly turning into gas that collects beneath the dust. This gas can escape through cracks or fractures in the surface, but the escape remains limited at this distance. The structure of the nucleus also contains multiple layers of ice that formed under different conditions. Some layers contain more volatile ices such as carbon monoxide, which sublimate at lower temperatures. These ices may begin to sublimate earlier than water ice, contributing small amounts of gas to the outer regions of the nucleus. The presence of more volatile ices helps shape the early stages of activity by creating pockets of gas that gradually weaken the dust coverage. Deeper within the nucleus, the temperature remains extremely low because sunlight penetrates only the outermost layers. These deeper regions retain their original structure, with ices and dust grains preserved in the same state they held during their long residence in the Oort Cloud. The interior remains insulated from external changes due to the low thermal conductivity of the ice-dust mixture. The nucleus is not uniform in its structure. The aggregation of ices and dust during formation created regions with varying density and porosity. Some areas contain loosely packed grains, while others contain more compact clusters. This variation influences how heat travels through the material and how gas escapes when sublimation begins. The porous structure also provides pathways for gas to move from the interior to the surface. These pathways form naturally due to the arrangement of the grains. When gas begins to form beneath the dust layer, it moves along these paths, finding openings where it can escape into space. At this stage in Leonard's journey, the gas escapes slowly and does not form visible features, but it begins to loosen the dust layer and modify the surface. The dust grains within the nucleus vary in size. Some are microscopic particles that attach to the ice through electrostatic forces or freeze within the ice. Others are larger grains that form clusters within the structure. These grains influence how sunlight is absorbed and how heat distributes across the surface. The darker grains absorb more sunlight, creating localized warming. The lighter grains reflect more light, reducing the warming effect. This interaction between dust and ice creates a complex pattern of thermal behavior across the nucleus. The structure of the nucleus also contains fractures that formed as the ice expanded or contracted during earlier passages near the sun. These fractures run through layers of ice and dust, providing channels for gas movement. As Leonard approaches closer to the sun, the fractures will play an important role in controlling the direction and strength of gas release. At this stage, however, the fractures remain dormant, with only small amounts of gas travelling through them. The early warming of the nucleus occurs gradually. The dust layer responds first, heating slowly as sunlight reaches it. The ices beneath respond next, but only in thin surface layers. The deeper layers remain cold and untouched by the changes occurring on the surface. This pattern reflects the slow progression of thermal energy through the nucleus, a process that unfolds over long intervals as Leonard continues its inward motion. The structure of the ice itself influences how sublimation begins. Some regions contain compact ice that sublimates more slowly. Other regions contain more porous ice that allows gas to escape more easily. As a result, the earliest signs of activity appear in regions where the ice is more porous or where the dust layer is thinner. These regions begin to release small amounts of gas, altering the structure of the surface slightly. The surface contains irregular features created by the accumulation of dust and the uneven distribution of ice. Small depressions, shallow ridges, and rough patches reflect the long history of the nucleus in cold environments. These features influence how sunlight reaches the surface. Areas that face the sun directly warm more quickly than those in shadow. Over time, this differential heating will contribute to the development of jets and the formation of the coma. The structure of the nucleus contains clues about the early solar system. The dust grains reflect the composition of the protoplanetary disk and the chemical processes that shape the early stages of planet formation. The ices record the distribution of volatile compounds in the disk. These materials remain preserved within the nucleus and become accessible only when the warming process begins. The slow inward journey now places Leonard in a region where sunlight begins to reveal these materials. The warming increases the mobility of gas molecules within the ice. As the molecules gain energy, they move through the pores and fractures, creating the earlier signs of gas release. These movements prepare the nucleus for the visible activity that will occur once the comet moves into regions where sunlight becomes significantly stronger. Although the surface remains quiet, the structure of the nucleus is undergoing subtle changes that will soon influence the development of the coma. As Leonard continues its inward path, each day brings slightly more sunlight to the surface, gradually warming the dust and ice. The internal structure begins to respond as sublimation increases slowly in localized regions. These early changes represent the transition from a cold, inert body into one that will soon display the full range of cometary activity. The nucleus that formed billions of years ago now prepares for the processes that will shape its appearance during its passage through the inner solar system. As Comet Leonard continues its inward journey and the sun's light strengthens further, the earlier stages of outgassing begin to take shape on and just beneath the surface. The warming of the dust layer increases steadily, and the ices beneath it respond with greater sensitivity. Sublimation, which until now has occurred only in isolated patches, begins to spread outward across regions where sunlight reaches consistently. The change remains gradual, but it marks the transition from a nearly inert object into one that starts to release gas and dust into space. The dust coating absorbs sunlight more efficiently as the comet approaches the inner regions, and the increased energy allows the outer layers of ice to warm enough for sublimation to become more pronounced. Gas molecules form within the ice and begin to push upward through the porous structure. This gas seeks pathways to the surface, moving through fractures and channels formed during earlier cycles of heating and cooling. In areas where the dust layer is thinner or more loosely packed, the gas escapes more easily, lifting small dust grains with it. These grains rise only a short distance before settling again due to the still, modest level of outgassing. The escaping gas forms a thin and uneven layer around the nucleus, too faint to be seen from a distance, but strong enough to alter the surface slightly. In some areas, the escaping gas clears away loose dust, exposing patches of brighter ice beneath. In other regions, dust accumulates as grains fall back to the surface, creating slopes and small drifts. These early surface changes reflect the delicate balance between sublimation and the gravitational pull of the comet, which remains too weak to prevent dust from being lifted, but strong enough to draw much of it back. The rotation of the nucleus influences how these processes unfold. As Leonard rotates different regions of the surface, face the sun experiencing cycles of heating and cooling. Sublimation increases when a region faces the sun directly and decreases when it rotates into shadow. This cyclical pattern creates gradual shifts in the distribution of dust and gas across the surface. In some cases, the warming of one region may trigger sublimation in neighbouring areas as heat travels through the porous material. Although the conductivity of the surface remains low, the slow movement of energy contributes to the expansion of early activity across more of the nucleus. The early release of gas also begins to influence the motion of dust grains that lie loosely on the surface. Some grains detach from the surface when the gas beneath them rises. These grains travel upward before falling back down, landing in new positions. This activity begins the process of reshaping the surface, altering the distribution of dust, and leaving behind patterns that reflect the underlying thermal changes. Some slopes may begin to shift as grains move slowly under the influence of gas flow and rotation. The illuminated surface experiences slightly higher temperatures than regions in shadow. These differences create variations in the rate of sublimation. In areas where the surface warms more quickly, sublimation occurs earlier in the day. In shadowed regions, sublimation begins later, or may not occur at all. This pattern leads to changes in how gas flows around the nucleus. The gas escapes from the warmer regions, first forming weak streams that move outward from the surface. These early gas flows represent the initial stages of activity that will later give rise to the coma. At this distance, the gas remains too thin to form visible structures, but begins to shape the environment immediately around the nucleus. The sun's radiation also interacts with the earliest gas released from the comet. Ultraviolet light breaks down some of the gas molecules, creating a mixture of atoms and molecules that flow outward from the surface. The density of the gas remains low, and the outward flow remains weak, yet these processes represent the first steps in forming the expanding atmosphere that will become more prominent later. The rotation of the comet affects how the gas disperses. As the nucleus rotates, gas escaping from different regions combines in irregular patterns, producing a thin and uneven envelope. This envelope will later expand into the coma as the comet approaches regions where sunlight becomes strong enough to drive vigorous outgassing. Variations in the structure of the nucleus also influence the early stages of outgassing. In areas where the ice is more porous, gas forms and escapes more easily. In regions where the ice is more compact, the gas remains trapped until the warming becomes stronger. This difference in structure results in uneven activity across the surface. The earliest jets of gas may begin to appear, though at this stage they remain too weak to lift dust in visible streams. Instead, the gas gently moves dust grains and alters the surface in subtle ways. As the sublimation increases, the surface experiences changes that reflect the competing forces of warming dust movement and gravitational pull. Some areas of the dust layer may begin to crack as pressure builds beneath them. These cracks allow gas to escape more easily, accelerating the sublimation in localized regions. Over time, this process contributes to the formation of more pronounced features, such as pits or depressions that become visible as the comet approaches the inner solar system. The earliest jets may also begin to appear in regions where fractures provide pathways for gas to escape in narrow streams. These jets remain weak at this distance, and may not carry enough dust to become visible, yet they contribute to the gradual expansion of the thin layer of gas around the nucleus. As Leonard continues inward, the sunlight strengthens further. The increased energy accelerates sublimation, causing more gas to form within the ice. The gas flows outward with greater strength, carrying dust grains with it. These grains may now travel farther before falling back, contributing to the redistribution of material across the surface. The dust layer becomes thinner in some regions and thicker in others as the surface responds to the increasing thermal activity. The early stages of outgassing also reveal the presence of volatile ices that respond to modest warming. Carbon monoxide ice sublimates at lower temperatures than water ice, and its sublimation begins earlier in the inward journey. The gas released from carbon monoxide contributes to the earliest activity. As Leonard moves closer to the sun, the sublimation of carbon dioxide and water ice will become more significant, strengthening the outgassing and leading to the formation of a visible coma. At this stage, the gas envelope remains confined close to the surface with no visible tail forming. The structure of the coma depends on the balance between gas escaping from the nucleus and the forces acting upon it, including the sun's radiation and the solar wind. When the outward flow of gas becomes strong enough, the material will expand to form the characteristic cloud that surrounds the nucleus. The early outgassing represents the transition from an inert nucleus to an active comet. The increase in sunlight marks the beginning of a series of changes that will reshape the surface and create the environment that will later expand into a visible coma. These changes occur gradually and reflect the slow, steady influence of sunlight as Leonard moves toward the inner regions of the solar system. As the comet continues its journey, the increasing sublimation will build upon these early stages, eventually producing the full range of activity that characterizes its passage near the sun. As Comet Leonard moves farther into the inner regions of the solar system, the increasing sunlight drives a steady rise in activity around the nucleus, causing the formation and growth of the coma. the expanding cloud of gas and dust that surrounds the comet. The coma develops as sunlight penetrates deeper into the layers of ice beneath the dust coating, warming the ices enough for sublimation to accelerate. Gas molecules form within the ice and flow outward, carrying with them dust grains that detach from the weakened surface. These grains travel into space, creating a diffuse envelope that grows with time. The coma first appears as a thin region surrounding the nucleus, but it expands outward as more gas and dust escape. The boundary of the coma becomes defined by the balance between the outward flow of gas and the forces acting upon it, including sunlight, solar wind, and the gravitational pull of the nucleus. In this region, the gravitational pull remains extremely weak, unable to keep dust grains from travelling outward once they detach. As the outgassing increases, the coma begins to take shape in a pattern influenced by the rotation of the nucleus. The rotation causes different regions of the surface to experience cycles of sunlight and shadow. The variations in temperature influence the rate at which gas forms and escapes. Areas facing the sun directly release gas more vigorously, while areas in shadow release less. As the nucleus rotates, jets of gas emerging from different locations contribute to the irregular shape of the coma. These jets strengthen as the distance to the sun decreases. Some regions of the nucleus contain fractures or porous ice that allow gas to escape in narrow streams. These streams carry dust grains with them, creating localized features in the coma. Although these features may not yet be visible from a distance, they help shape the distribution of gas and dust within the expanding envelope. The coma grows as sunlight continues to warm the nucleus. The outgassing increases and the dust grains carried outward begin to settle into patterns determined by the flow of gas and the direction of sunlight. The gas escapes the nucleus with gentle acceleration, moving outward into space where it slows and disperses. The dust grains respond differently based on their size and mass. Smaller grains travel farther on the outflow of gas, while larger grains remain closer to the nucleus. The mixture of gas and dust creates a layered structure within the coma. The gas forms the outer regions, expanding freely until it dissipates into space. The dust remains more concentrated in the inner regions, creating a region of greater density near the nucleus. These patterns shift continually as new gas and dust enter the coma, and older material disperses. The sunlight not only warms the ices but also interacts with the gas molecules within the coma. Ultraviolet radiation breaks down some of the gas molecules, creating new atomic and molecular species that contribute to the chemistry of the coma. The density of the gas remains highest near the nucleus and decreases with distance. As the coma expands, it becomes influenced more strongly by the solar wind, the flow of charged particles from the sun. The solar wind begins to shape the coma, altering the paths of ionized particles and influencing the early development of the ion tail. At this stage, the coma remains primarily influenced by the gas escaping from the nucleus, but the solar wind begins to play a larger role as the comet moves closer to the sun. The flow of the solar wind interacts with the gas molecules, creating a boundary where the solar wind pressure balances the pressure of the outflowing gas. This boundary shifts as the comet moves, responding to the strength of the solar wind and the rate of outgassing. Within the coma, the dust grains reflect sunlight and scatter it into space, making the coma increasingly bright as more material escapes from the nucleus. The increasing brightness reflects the growing volume of gas and dust surrounding the nucleus. As the coma expands, it becomes visible from greater distances, allowing observers to detect the comet even before the tails fully develop. The size of the coma increases rapidly as the comet approaches the region near the sun, where sublimation becomes more vigorous. The exact size depends on the rate of gas release and the speed at which the gas expands. In some regions of the coma, dust grains interact with sunlight differently based on their composition and size, creating subtle differences in the brightness and distribution of the coma. The rotation of the nucleus continues to influence the structure of the coma. As different regions of the surface release gas at different rates, the coma develops asymmetries that reflect the distribution of active areas. Some areas may release gas continuously, while others release gas intermittently as sunlight moves across the surface. These variations create changing patterns within the coma, with streams of gas and dust forming and dispersing over time. The coma also interacts with the gravitational pull of the Sun. As Leonard moves closer, the Sun's gravity influences the trajectory of dust grains within the coma. Smaller grains respond more readily to the forces of sunlight and the solar wind, while larger grains respond more strongly to gravity. These differences in response create layers within the coma, where dust of different sizes becomes concentrated. The coma represents the intermediate stage of Leonard's transformation from an inert object into a fully active comet with visible tails. The formation of the coma reflects the combined effects of sunlight rotation sublimation and the structure of the nucleus. The coma will continue to expand as Leonard approaches regions where the sunlight becomes strong enough to drive more vigorous outgassing. At this stage, the nucleus remains the central source of the coma. The gas and dust continue to escape, creating the growing envelope that surrounds the comet. The coma expands outward until it reaches a size determined by the balance of forces acting upon it. The shape and size of the coma continue to change as Leonard approaches the Sun. The outgassing increases significantly with distance, creating stronger jets and a larger volume of gas. The dust carried outward begins to form structures that will contribute to the dust tail. The gas interacts with the solar wind, creating charged particles that will contribute to the formation of the ion tail. These processes remain in their early stages, but they lay the foundation for the visible activity that will soon emerge. As Leonard moves closer to the Sun, the coma will grow larger and brighter, marking the transition into a stage where the comet becomes an active participant in the dynamic environment of the inner solar system. The growing envelope of gas and dust reflects the increasing influence of sunlight on the nucleus, shaping the appearance and structure of the comet as it approaches the warmest portion of its orbit. As Comet Leonard continues its inward passage and the coma expands into a broader envelope of gas and dust, the conditions become favourable for the formation of the dust tail, a structure shaped primarily by the interaction between sunlight and the small particles released from the nucleus. The dust tail emerges as a distinct feature once the outward flow of dust grains becomes strong enough for sunlight to push these grains into elongated paths that extend away from the comet. The dust grains vary in size, composition and reflectivity, and each grain responds differently to the forces acting upon it. The smallest grains are influenced strongly by sunlight, while larger grains respond more to the gravitational pull of the comet and the Sun. The earlier stages of the dust tail begin when sunlight reaches the coma with enough intensity to exert radiation pressure on the dust grains. Radiation pressure is the force produced when light interacts with particles, transferring energy and momentum. The smaller dust grains, which weigh very little, experience the greatest influence. These grains begin to accelerate away from the nucleus, moving along curved paths that gradually align into a tail oriented away from the Sun. Larger grains remain closer to the nucleus and follow slower, more curved trajectories. The dust tail forms from this distribution of particles, gradually stretching outward as new dust continues to escape from the surface. The rotation of the nucleus influences the direction and distribution of dust within the coma, which in turn affects the initial shape of the dust tail. Areas of the surface that release dust more actively contribute larger numbers of grains to the flow. These regions may align with fractures or porous zones where sublimation occurs more vigorously. As these regions rotate into sunlight, they release dust into the coma, and as they rotate away, the release decreases. Over time, this rotational pattern creates asymmetries in the dust tail, with some regions appearing denser or more extended than others. As Leonard approaches the inner regions, the dust tail becomes more pronounced. The intensity of sunlight strengthens, increasing the force of radiation pressure on the dust grains. This causes the smallest grains to accelerate more quickly, extending the dust tail farther into space. The increased outgassing from the nucleus releases more dust, contributing to the growing complexity of the tail. The dust grains interact with sunlight not only through radiation pressure but also through scattering and reflection, making the dust tail bright and visible across large distances. The brightness depends on the number and size of dust grains as well as the angle of sunlight. The dust grains scatter light in all directions, but the density of the dust tail determines how much light reaches observers in different regions of space. The dust tail gradually takes on a curved shape due to the combination of the comet's motion and the influence of radiation pressure. The comet continues to move along its orbit, while the dust grains travel outward along paths shaped by the balance of forces. This creates a structure that widens as it extends away from the nucleus. The dust tail does not point directly away from the Sun, but curves slightly, reflecting the motion of the comet as it travels along its orbital path. The dust tail also contains variations in density and particle size. Near the nucleus, the dust density remains high because grains have had less time to disperse. Farther from the nucleus, the dust becomes more diffuse as particles spread out. This gradient creates a tail that appears bright near the nucleus and gradually fades with distance. The structure of the dust tail changes continually as new dust enters the flow and older dust disperses. Some regions of the tail may appear denser if the comet releases dust more vigorously during specific periods of rotation. These variations are influenced by the distribution of sunlight across the surface, the orientation of the comet's rotation, and the presence of fractures that act as vents for gas and dust. As sunlight warms the nucleus more strongly, the sublimation rate increases, releasing more dust into the tail. The dust grains that leave the surface carry with them traces of the early solar system. These grains formed from minerals and carbon-rich compounds that condensed in the protoplanetary disk. They have remained preserved within the icy matrix of the nucleus for billions of years. As they enter the dust tail, they become exposed to sunlight for the first time. The structure of the dust tail contains information about the composition and origin of the comet. By observing the brightness and distribution of the dust, scientists can infer the size and composition of the grains. Some grains scatter sunlight more effectively due to their reflective surfaces, while others absorb more light due to their darker compositions. The dust tail also interacts with the solar wind. Although the dust grains are mostly unaffected by the charged particles in the solar wind, the gas in the coma may influence how the dust moves. The gas flows outward from the nucleus, creating streams that interact with the dust and alter its trajectory. These interactions contribute to the shape and texture of the dust tail. The tail continues to extend as Leonard moves closer to the Sun. The increased rate of sublimation releases more dust, strengthening the tail. The combination of radiation pressure, gas flow, and the comet's motion produces complex patterns within the dust tail that evolve over time. The tail becomes one of the most recognizable features of the comet, visible across long distances and reflecting the increasing activity of the nucleus. As Leonard continues its inward journey, the dust tail becomes longer, brighter, and more dynamic. The dust grains continue to move outward, forming a trail that extends for long distances. The tail remains oriented away from the Sun, following the path shaped by sunlight and the motion of the comet. As the comet approaches regions where sunlight is strongest, the dust tail reaches its maximum length and brightness. This stage marks the full development of the dust tail, showing the transformation of Leonard from a distant icy body into an active comet surrounded by gas and dust. The formation of the dust tail reflects the combined influence of sunlight, the structure of the nucleus, and the dynamic environment of the inner solar system. The dust grains carry with them the chemical and mineralogical history of the early solar system, revealing information about the conditions under which the comet formed. As Leonard approaches the Sun, the dust tail becomes a visible record of its ongoing transformation, shaped by the forces acting upon the comet and the materials it carries. The dust tail continues to evolve as new dust enters the flow and older dust disperses into space. The structure reflects the gradual increase in activity and the influence of sunlight on the comet. As Leonard moves toward perihelion, the dust tail will continue to expand and brighten, marking one of the most active periods in the comet's orbit. As Comet Leonard draws still closer to the Sun, the growing influence of solar radiation and the solar wind causes the ion tail to form and extend outward from the nucleus. Unlike the dust tail, which develops from solid particles pushed away by sunlight, The ion tail emerges when gas molecules escaping from the nucleus interact with ultraviolet radiation and become ionized. These ionized particles then respond strongly to the flow of charged particles in the solar wind, creating a tail that points almost directly away from the sun regardless of the comet's direction of travel. The formation of the ion tail begins when ultraviolet radiation from the sun penetrates the expanding coma and reaches the gas released by sublimation. The ultraviolet radiation breaks apart some of the gas molecules, producing ions that carry electric charge. These ions include fragments of water molecules, carbon monoxide, carbon dioxide, and other volatile compounds. Once ionized, the particles no longer move freely within the coma. Instead, they become influenced by the magnetic field carried by the solar wind. The solar wind flows outward from the sun at high speed, carrying with it a magnetic field that extends across the solar system. When the ionized particles from the coma encounter this magnetic field, they follow paths shaped by the field lines. This interaction accelerates the particles and directs them outward in a narrow stream that forms the ion tail. The ion tail begins to stretch away from the nucleus as soon as these interactions take place. The earliest portion of the tail remains faint because the number of ionized particles is still low at this distance. As Leonard moves closer to the sun, the amount of ultraviolet radiation increases, producing more ionized particles and strengthening the flow of gas into the tail. The structure of the ion tail differs significantly from that of the dust tail. The ion tail forms a narrow, straight feature that points almost directly away from the sun. This direction reflects the motion of the charged particles as they move along magnetic field lines in the solar wind. The dust tail, by contrast, curves due to the influence of the comet's motion and the different trajectories of dust grains. The two tails may diverge visibly as Leonard continues inward, with each tail shaped by different physical processes. Within the ion tail, the density of particles varies depending on the rate of sublimation and the strength of the solar wind. Stronger solar wind enhances the flow of ions, extending the tail farther and increasing its brightness. Weaker solar wind produces a shorter or fainter ion tail. These variations reflect the dynamic environment near the sun, where the conditions of the solar wind change over time. The ion tail also reflects the structure of the coma. In regions where sublimation produces greater amounts of gas, the ion tail begins with a denser region of ionized material. The rotation of the nucleus influences the distribution of gas within the coma, and these variations carry into the ion tail. As different regions of the surface release gas at different times during the rotation, the ion tail may show subtle patterns that reflect these cycles. The ion tail grows rapidly as Leonard travels closer to the sun. The increasing sublimation rate releases more gas, and the ultraviolet radiation intensifies. The ionization rate rises, producing more particles that respond to the solar wind. The resulting tail extends across large distances and becomes visible as a distinct feature of the comet. The brightness of the ion tail depends on the density and composition of the ionized particles, as well as the intensity of the solar wind. The ionized particles emit light when they interact with sunlight, creating the characteristic glow of the ion tail. As more material enters the tail, the structure becomes more defined, showing a narrow central stream and surrounding regions of more diffuse ionized gas. These regions shift in shape and brightness as the flow of gas from the nucleus changes. The solar wind continues to influence the ion tail, shaping the position and direction of the particles. Stronger solar wind can compress the tail or alter its angle slightly. If the solar wind varies rapidly, the ion tail may show changes along its length, such as bends or irregularities. These variations reflect the dynamic environment through which Leonard travels. As Leonard approaches perihelion, the point in its orbit where it comes closest to the sun, the increase in sunlight and solar wind produces the most intense period of ion tail formation. The sublimation rate reaches its peak, releasing large amounts of gas from the nucleus. Ultraviolet radiation ionizes much of this gas, producing a dense flow of charged particles. The solar wind accelerates these particles outward, forming a long, bright tail that extends far behind the comet. The ion tail responds more quickly to changes in the environment than the dust tail does. If the solar wind strengthens suddenly, the ion tail shifts and aligns more directly with the flow of charged particles. If the solar wind weakens, the tail may become more diffuse. The dust tail, by contrast, responds more gradually because it consists of particles with greater mass. The differences between the two tails become clearer as the comet moves closer to the Sun. The dust tail curves gently due to the comet's motion and the forces acting on the dust grains. The ion tail extends in a straight line away from the Sun, shaped almost entirely by the solar wind. These contrasting patterns reveal the different physical processes shaping each tail. The structure of the ion tail contains information about the composition of the gas released from the nucleus. Different ions emit light at different wavelengths, revealing the presence of various substances within the comet. The strength of these emissions depends on the density of the ionized particles and the intensity of the sunlight. As Leonard moves closer to the Sun, the emissions strengthen, providing insight into the distribution of materials within the nucleus. The ion tail continues to evolve as the comet approaches perihelion. The increased heat causes more sublimation, releasing more gas into the coma. The ionization process intensifies, and the solar wind continues to accelerate the charged particles outward. The tail grows longer and brighter, revealing the full extent of the comet's activity during its closest approach to the Sun. At this stage, the ion tail becomes one of the most dynamic features of the comet. Its shape changes rapidly in response to variations in the solar wind and the rotation of the nucleus. The length of the tail can extend far into space, and its brightness reflects the level of activity within the coma. The formation of the ion tail marks a key stage in Leonard's journey, showing the transformation of the comet as it moves into the most energetic region of its orbit. The interactions between sunlight, solar wind, and the materials escaping from the nucleus create a structure that changes, continually shaped by the forces of the inner solar system. As Leonard moves toward the next stage of its inward passage, the ion tail will continue to grow and evolve, reflecting the increasing activity of the comet as it approaches the point of closest approach to the Sun. As Comet Leonard approaches its closest distance to the Sun, the increasing intensity of sunlight and solar wind drives the nucleus into its most active phase, creating a complex environment where gas dust and charged particles flow outward in continuous motion. At this stage, the surface of the nucleus experiences stronger heating than at any earlier point in the comet's journey. The warming affects not only the outermost layers of dust, but also the deeper regions of ice that remained insulated during the earlier phases of the inward passage. These deeper layers contain volatile materials that sublimate quickly once exposed to sufficient sunlight, producing stronger jets and increasing the overall rate of outgassing. The surface of the nucleus undergoes rapid change as the warming penetrates deeper into its structure. Some regions contain pockets of gas trapped beneath the dust, formed during earlier warming cycles. As the temperature rises, these pockets expand and push upward, causing the dust layer to weaken or break apart. When the dust layer ruptures, the heated gas escapes into space in a sudden release that forms narrow jets. These jets carry dust grains with them and contribute significantly to the formation of the surrounding coma. The jets appear in regions where fractures or porous ice provide pathways for gas to escape. As sunlight continues to heat the surface, the number and strength of these jets increase. The rotation of the nucleus causes the jets to sweep across different regions of the coma, creating curved or spiral patterns within the expanding cloud of gas and dust. These patterns shift continually as the rotation brings different active areas into sunlight. The regions of the nucleus that face the Sun most directly produce the strongest jets. The intensity of sunlight in these regions warms the surface quickly, causing rapid sublimation of both water ice and more volatile substances. The escape of gas from these regions contributes to the growth of the coma and feeds both the dust and ion tails. The strength of the jets depends on the structure of the ice, the thickness of the dust coverage, and the internal arrangement of cracks and cavities. As the surface becomes more active, some regions may erode faster than others. Erosion occurs when jets remove dust and ice from the surface, carrying the material outward into the coma. Over time, this difference in erosion can create pits or depressions in the surface. These features may grow larger as the nucleus continues to release material near perihelion. The interior of the nucleus responds to the increasing heat by allowing deeper layers of ice to sublimate. This process increases the internal pressure and creates new cracks that open pathways for gas to escape. The newly formed cracks allow sunlight to reach deeper layers, accelerating the sublimation process. These changes represent the dynamic transformation of the nucleus during its closest approach to the Sun. The increased sublimation releases large amounts of water vapor and other gases into the coma. The gas expands rapidly and interacts with the dust grains in the surrounding region. This interaction contributes to the density and structure of the coma, making it larger and brighter. The brightness reflects the increasing amount of dust and gas surrounding the nucleus, and the strong sunlight illuminating these materials. The growing activity also contributes to the formation of the tails. The dust tail becomes longer and broader as more dust grains enter the outward flow. The ion tail becomes brighter as more gas is ionized by ultraviolet radiation. The solar wind accelerates these charged particles away from the nucleus, creating a long, straight tail that extends across large distances. At perihelion, Leonard experiences the strongest forces of sunlight and solar wind during its orbit. The temperature of the surface increases rapidly, causing the sublimation of water ice to reach its maximum rate. The gas flow becomes strong enough to lift larger dust grains from the surface, contributing to the density of the dust tail. The jets grow stronger, releasing material in streams that change direction as the nucleus rotates. The pressure created by the escaping gas exerts a small but measurable force on the nucleus. This force can influence the rotation period of the comet, slightly causing small changes in how the nucleus turns. These changes occur gradually and reflect the interaction between the flow of gas and the underlying structure of the nucleus. The increased activity near perihelion causes the coma to expand rapidly. The gas flows outward in all directions, carrying dust grains with it. The dust remains more concentrated near the nucleus, while the gas moves outward until it becomes part of the surrounding tails. The coma becomes dense enough to influence how sunlight reaches the nucleus, creating a dynamic interplay between incoming radiation and the material escaping from the surface. The solar wind interacts strongly with the ionized particles in the coma. As the solar wind accelerates these particles outward, the ion tail grows in length and brightness. The structure of the ion tail may show shifting patterns due to variations in the solar wind. Regions of stronger solar wind can shape the tail more sharply, while weaker regions may allow the tail to disperse more widely. As Leonard continues its passage near perihelion, the rate of sublimation remains high. The nucleus sheds large amounts of material each day, altering the surface and contributing to the overall activity of the comet. The dust and gas that escape from the nucleus represent materials preserved for billions of years, now released into the inner solar system. After reaching its closest point to the Sun, Leonard begins to move away, and the sunlight begins to weaken. However, during the period immediately after perihelion, the nucleus remains warm enough to maintain high levels of activity. The gas trapped in deeper layers continues to escape, and the surface remains warm enough to allow sublimation to proceed even as the Sun's intensity decreases. This phase represents a continuation of the strong activity observed at perihelion. As Leonard moves farther along its orbit, the surface gradually cools. The jets begin to weaken as the supply of sublimating ice decreases. The coma begins to contract as the flow of gas slows. The dust and ion tails remain visible for some time, carried outward by the forces that shaped them earlier. The period after perihelion marks the beginning of the decline in activity, but the transformation of the nucleus remains evident. The surface now contains new features created during the peak activity, including pits, fractures, and regions where dust has been redistributed. Some of these features may influence how the nucleus behaves during future passages. The strong activity near perihelion reflects the interplay of sunlight, solar wind, and the structure of the nucleus. The increase in sublimation reveals the composition of the deeper layers, while the formation of jets and tails shows how the comet interacts with the dynamic environment of the inner solar system. As Leonard continues its outward motion, the peak activity begins to subside, but the changes to the nucleus remain, marking the end of its most active and energetic phase. As Comet Leonard travels beyond perihelion and begins the long outward arc of its orbit, the environment around the nucleus gradually changes as the heat absorbed during its closest approach to the Sun dissipates. The decline in solar energy occurs slowly at first, allowing the recently warmed layers of ice beneath the dust to continue sublimating for some time. This sustained sublimation maintains a level of activity that, while weaker than at perihelion, remains higher than anything observed during the inward passage. The nucleus now carries the effects of the intense heating it experienced near the Sun. Portions of the dust layer have been eroded or rearranged by jets exposing fresh pockets of ice that continue to sublimate. Other regions contain newly formed cavities where dust was lifted and carried into the coma. These cavities alter how sunlight interacts with the surface, creating irregular patterns of heating that influence the rate of sublimation as the comet moves outward. The heat that penetrated the nucleus during perihelion continues to flow toward cooler regions, affecting layers that were not previously exposed to significant warming. These deeper layers may now begin to release gas, even though the surface is cooling. This release occurs through fractures and channels created during earlier periods of intense activity. As the gas escapes, it produces weaker jets that help maintain the coma. The rotation of the nucleus continues to shape where sublimation occurs. Regions that received the strongest sunlight before perihelion may now cool more slowly, prolonging their activity. Other regions that spent less time in sunlight may cool more quickly and experience reduced sublimation. The distribution of activity shifts gradually as the balance of heat across the surface changes. The coma, which reached its maximum size near perihelion, begins to contract gradually as the flow of gas decreases. The dust grains that once filled the coma in large numbers now drift outward, leaving behind a thinner envelope of material. The gas continues to expand away from the nucleus, but at a slower rate than before. This reduction in activity marks the gradual transition from the peak of outward energy release to a more subdued phase. The dust tail continues to extend behind the comet, but the density of grains decreases as fewer are released from the surface. Larger grains that were lifted during perihelion may now travel along paths shaped mainly by the comet's motion and gravity, forming a broader and more diffuse trail. Smaller grains, influenced by sunlight and radiation pressure, disperse more widely and gradually fade from view as they travel through space. The ion tail remains active for a time after perihelion, as the gas in the coma continues to become ionized by ultraviolet radiation. The solar wind continues to accelerate these charged particles outward, forming a tail that points away from the Sun. However, as the flow of gas weakens, the ion tail becomes less dense and begins to fragment. Variations in the solar wind can cause portions of the ion tail to bend, shift, or break apart, creating a dynamic structure that changes from day to day. The decline in activity also affects the pressure exerted by gas escaping from the nucleus. Near perihelion, this pressure caused small adjustments to the rotation of the comet. As the outward flow of gas weakens, this influence diminishes, allowing the rotation to stabilize. However, the changes made during the most active period remain recorded in the comet's motion. The outward flow of material reveals more of the structure beneath the surface. Layers of ice that once lay hidden beneath the dust are now exposed and altered by the heat absorbed near the Sun. Some layers become brittle due to thermal stress, forming cracks that influence the path of future outgassing. Other regions contain pockets of dust left behind as the ice beneath them sublimated. These pockets may collapse, creating small depressions or pits. The outward motion of the comet carries it into regions where sunlight decreases steadily. The decline in warmth slows the sublimation process. Areas that once released large amounts of gas now produce weak streams or none at all. The dust layer begins to settle into a more stable configuration as the forces lifting it weaken. Some dust falls back onto the surface, covering exposed ice and reducing further sublimation. As the comet travels farther from the sun, the balance between sunlight and the cold environment begins to reverse. The nucleus starts to cool more quickly than it warms. The heat that reached deeper layers dissipates, gradually reducing the internal pressure and weakening the jets. The coma contracts further as the rate of gas release declines. The tails begin to fade as fewer particles enter them. The environment around Leonard becomes calmer. The strong forces of sunlight and solar wind that shape the comet near perihelion now exert less influence. The expanding coma thins until it becomes a faint cloud surrounding the nucleus. The dust tail disperses into space, leaving a diffuse trail of particles along the comet's orbital path. The ion tail shortens as the supply of ionized gas decreases. The decline in activity reveals the long-term effects of the comet's encounter with the inner solar system. The surface now contains new features formed by sublimation and erosion. Some regions show smoother surfaces where dust settled. Others contain rough, fragmented terrain created by collapsing cavities. These changes reflect the dynamic nature of the comet's response to sunlight. As Leonard moves toward the outer regions again, the environment becomes cold enough to halt sublimation completely. The remaining gas in the coma escapes into space, and the last dust grains fall back onto the surface or drift away. The coma fades until the nucleus stands alone once more. The surface cools to the low temperatures characteristic of the outer solar system. The fresh features formed during the comet's passage through the inner regions become frozen in place. The volatile materials that remain beneath the dust layer return to a solid state. The fractures and cavities created during perihelion become dormant until the comet travels inward again. Leonard's outward journey reflects the natural cycle of cometary behaviour. The nucleus responds to sunlight in predictable ways, heating near perihelion, releasing gas and dust, forming a coma and tails, and then cooling as the comet moves away. These processes unfold across long intervals and reveal the interplay between the structure of the nucleus and the environment of the inner solar system. As the comet continues outward, the changes that occurred during its closest approach remain preserved, marking the surface with features that may influence future passages. The decline in activity marks the transition into a quieter phase of the orbit, where the nucleus will continue its outward motion toward the cold, remote regions from which it once emerged. As Comet Leonard moves deeper into the outward portion of its orbit, the cooling of the nucleus continues at a steady pace, allowing the materials within it to transition gradually back toward the stable conditions that define the outer regions of the solar system. The sunlight that once penetrated the dust and ice with enough intensity to drive vigorous sublimation now weakens steadily. The thermal energy accumulated during perihelion begins to dissipate through the porous layers of the nucleus, moving outward toward the surface, where it radiates into space. This gradual loss of heat allows the volatile ices that had become active during the inward and perihelion phases to refreeze in the deeper layers, restoring some of the structure that had been temporarily altered by the intense warming. The surface of the nucleus remains marked by the activity that occurred near the sun. Regions that were once heated strongly now cool at different rates, depending on their exposure to sunlight during perihelion. Some areas retain warmth longer due to their orientation or the thickness of the dust that covers them. Others cool more quickly because their surfaces were stripped of dust, leaving exposed ice that radiates heat more efficiently. The combination of cooling rates produces a patchwork of thermal states across the nucleus, each influencing how the surface evolves as the comet continues outward. The jets that once released strong flows of gas now weaken significantly. The underlying ice no longer receives enough energy to sublimate at a high rate. Sublimation continues only in the deepest layers where heat lingers, but even this activity fades as the temperature decreases. Small amounts of gas may escape through fractures that were widened during perihelion, but the flow lacks the strength to carry dust grains far from the surface. This reduced outgassing allows the surface to stabilize. Dust that once floated above the nucleus or drifted outward now settles slowly onto the terrain. Larger grains fall back, first landing in nearby regions and forming new layers that cover the exposed ice. Smaller grains may travel slightly farther, carried a short distance by the lingering gas flow before settling. This redistribution of dust begins to create a new surface layer that will insulate the nucleus during the remainder of the outward journey. As the gas flow weakens, the coma contracts steadily. The gas molecules that once filled the space around the nucleus now disperse into the surrounding region, leaving behind only a thin atmosphere that becomes increasingly difficult to distinguish from the vacuum of space. The density of dust within the inner coma decreases as fewer grains enter the flow. Eventually, the coma reaches a point where it no longer expands meaningfully and begins to fade until only the nucleus remains visible. The dust tail, which had extended across great distances near perihelion, begins to separate from the comet as the nucleus ceases to release new grains. The tail continues to drift outward along the orbital path shaped by radiation pressure and the gravitational influence of the Sun. Over time, the dust disperses into space, leaving only a faint trail of particles that mark the comet's passage. These particles gradually spread out until they become part of the general distribution of dust in the inner solar system. The ion tail fades more quickly than the dust tail. Without a steady supply of ionized gas from the nucleus, the tail cannot maintain its structure. The remaining ions disperse rapidly due to the influence of the solar wind. Small fragments of the ion tail may persist for a short time, but they eventually become indistinguishable from the surrounding solar wind environment. The fading of the tails marks the final phase of Leonard's active period. With the major sources of activity now diminished, the nucleus transitions into a quieter state. The cooling surface begins to stabilize as dust settles evenly across the terrain. Cavities created during periods of intense sublimation may collapse under their own weight, redistributing dust and ice into new configurations. Some regions may form crusts where layers of dust become compacted through repeated cycles of heating and cooling. These crusts help insulate the underlying ice, slowing further changes. The return to cooler conditions allows the volatile ices beneath the surface to refreeze. This process restores some of the integrity of the nucleus, though the internal structure remains altered by the cracks and cavities formed during periods of high activity. These features become dormant but remain ready to influence future cycles of sublimation during subsequent passages near the Sun. The outward journey also brings Leonard into a region where the Sun's gravitational influence becomes less dominant compared with the inward phases. The comet's speed gradually decreases as it climbs away from the Sun's gravitational well. The motion remains smooth and predictable, guided by the parameters of the orbit established long before its most recent passage through the inner solar system. The decreasing sunlight reduces the influence of radiation pressure and weakens the forces that once shaped the tails. As these forces diminish, the environment around the comet becomes calmer. The space surrounding Leonard takes on the characteristics of the outer solar system, where temperatures remain low and activity remains minimal. The nucleus stabilizes into a state defined by the balance between its internal structure and the surrounding cold environment. The dust that now covers the surface helps to preserve the remaining ices by reflecting sunlight and insulating the underlying layers. This insulation slows further changes and allows the nucleus to cool uniformly. The reduced temperature also lowers the mobility of any remaining gas molecules, preventing further sublimation, except in isolated pockets where heat may linger. As Leonard continues outward, the influence of the solar wind decreases. The density of the charged particles in the solar wind becomes lower at greater distances, and the interactions that once shaped the ion tail become negligible. The comet moves through a region where the solar wind exerts only gentle forces on the remaining traces of gas and dust. The changes that occurred during perihelion remain imprinted upon the nucleus. The pits formed by collapsing cavities, the fractures created during rapid sublimation, and the redistributed dust that settled across the surface all remain as markers of the comet's recent journey. These features will persist until the next inward passage, when sunlight will once again interact with the nucleus and reshape its surface. The outward journey reflects the cyclical nature of cometary behavior, where intense activity near the Sun gives way to long periods of calm in the outer regions. Leonard's path leads it into the colder areas of the solar system, where the environment once again preserves the nucleus in a state similar to the one it held before the inward passage. As the comet moves toward the outermost parts of its orbit, the last traces of activity fade completely. The dust settles, the gas disperses, the nucleus cools until it reaches the temperatures characteristic of the distant solar system. The features left behind reveal the history of the comet's recent encounter with the Sun, providing a record that will remain frozen in place until the next cycle begins. As Comet Leonard continues its outward trajectory and the warmth of the inner solar system diminishes further, the nucleus enters a phase of deep cooling that gradually restores the conditions that dominated its long residence in the distant regions from which it came. The sunlight that once drove vigorous sublimation now weakens to the point where its influence reaches only the outermost dust grains. With each passing day, the temperature across the surface drops, allowing the volatile ices beneath the dust to return fully to their solid state. This transition occurs at different rates across the nucleus, influenced by the depth to which heat penetrated during perihelion and the distribution of fractures formed when the comet released gas. The dust layer, once disturbed by jets and outflows of material, now settles into a more stable covering. Grains that were suspended briefly in the thinning coma fall back onto the surface in a slow, steady drift. Larger grains settle first, forming a coarse layer across the regions where activity once surged. Smaller grains continue to travel for longer periods before landing, dispersing across the terrain in a fine coating that smooths the underlying features. Over time, these grains merge into a uniform layer that seals many of the fractures exposed during perihelion and insulates the remaining volatile ices from the faint sunlight that reaches the comet. The internal structure of the nucleus cools from the inside outward. The deeper layers warmed during perihelion release residual heat into the surrounding environment at a slow rate. This release creates gentle flows of energy that pass through the porous structure before radiating into space. As these flows diminish, the inner pockets of gas formed during the active phase now refreeze, restoring the mechanical strength of the nucleus. Some cracks close slightly as the refreezing of water ice expands the material, while others remain as dormant features that will influence future activity during subsequent inward passages. The outward motion of Leonard also changes the balance of forces acting on the nucleus. The decreasing intensity of the solar wind reduces the effects that once shaped the ion tail. The charged particles released near perihelion disperse into the surrounding space carried by the solar wind until they blend into the broader environment of the inner solar system. Without new ionized material feeding it, the ion tail fades completely, leaving no visible trace near the comet. Only the faint trail of dust released during the active period persists for a longer time, gradually thinning as larger grains drift along the orbital path and smaller particles disperse under the influence of radiation pressure. The coma continues to shrink as the escape of gas declines. In the earlier stages of the outward journey, the coma still contained enough gas to create a thin envelope around the nucleus. However, as the temperatures fall below the threshold for sublimation, the formation of new gas ceases. The remaining molecules escape into space, leaving the nucleus without the surrounding cloud that once signaled its presence. The surface of the nucleus now reflects the alterations created during its passage near the Sun. Depressions carved by jet slopes formed by collapsing pockets of ice, and regions stripped of dust by strong outflows remain frozen in place. Over time, the uniform settling of dust softens these features slightly, but many will remain etched into the structure until the comet experiences another inward passage. These features record the specific conditions of this particular orbit, creating a map of the thermal and mechanical processes that shaped the comet during its most recent encounter with the Sun. As Leonard travels outward, the gravitational pull of the Sun weakens. The comet's speed decreases gradually as it climbs toward the farthest point of its orbit. The path remains smooth and predictable, defined by the same forces that guided it inward. The lack of significant outgassing removes the small accelerations once produced by the jets, leaving the orbit unaffected by internal forces. This stability allows the comet to drift quietly into the colder regions, where temperatures remain low and activity remains absent. The dust layer that now covers the nucleus plays an important role in protecting the volatile ices beneath. The thickness of this layer varies across the surface, shaped by the distribution of dust during and after perihelion. In some areas, the dust becomes compacted through repeated cycles of heating and cooling. These compacted regions form crusts that insulate the underlying ice more effectively than loose dust. In other areas, the dust remains loosely packed, allowing subtle thermal changes to penetrate more readily during future inward passages. The composition of the nucleus remains unchanged beneath the surface. The material preserved in the deeper layers continues to hold the chemical and mineralogical record of the early solar system. These layers remain unaffected by the brief period of intense heating during perihelion. As the outer surface stabilizes, the deeper structure becomes dormant, once more entering a state of preservation that will last through much of the outward journey. Leonard's interaction with the environment of the outer solar system becomes increasingly gentle. The decreasing sunlight no longer provides enough energy to alter the surface. The solar wind becomes less dense and exerts little influence on the few remaining grains of dust near the nucleus. The space through which the comet travels contains only sparse material, offering little resistance or disturbance. The nucleus continues outward with minimal interaction, maintaining a trajectory that reflects the long-term gravitational influence of the Sun. As the comet moves farther away, the heat absorbed during perihelion dissipates completely. The surface reaches temperatures low enough to halt all remaining sublimation. The dust that settles across the nucleus enters a state of near-permanent stability, disturbed only by the faint pressures of micrometeoroid impacts or the subtle forces of thermal cycling at great distances. These changes occur slowly unfolding across years as Leonard travels farther from the Sun. The transformation from an active comet into a dormant body becomes complete. The coma that once surrounded the nucleus disappears entirely. The tails that once extended across large regions of space fade until they are no longer visible. The surface cools to the temperatures characteristic of the distant outer solar system, preserving the features created during the recent active phase. The outward journey thus marks the beginning of a long period of quiescence. Leonard travels through regions where sunlight has little effect, allowing the nucleus to remain stable until it approaches the Sun again in the distant future. During this time, the materials that make up the nucleus remain preserved, protected beneath the dust layer and shielded from significant external influences. The comet continues along its orbit, moving steadily toward the farthest point from the Sun, where it will remain for many years before gravity gradually draws it inward once more. As Comet Leonard moves into the most distant stretch of its outbound trajectory, the environment around the nucleus becomes increasingly defined by deep, cold, faint sunlight and the slow restoration of the conditions that dominated its long past in the remote regions of the solar system. The energy that once drove vigorous activity near perihelion has now dissipated almost entirely. The nucleus cools further with each passing day, allowing both surface and subsurface materials to settle into stable states shaped by extremely low temperatures. The dust layer that blankets the nucleus becomes the primary barrier between the remaining volatile ices and the faint sunlight that reaches the comet. This layer, formed from grains lifted during earlier activity and redistributed across the surface, now compacts gradually under the influence of thermal contraction and the weak pull of the comet's gravity. Over time, this compaction strengthens the insulating properties of the dust, preventing residual heat from escaping too quickly, and shielding the underlying layers from any remaining solar warming. As the nucleus cools, the deeper layers that once held pockets of gas begin to contract. The water ice and other volatile ices that sublimated near perihelion refreeze gradually as the temperatures drop. This refreezing process influences the internal structure by pushing apart grains in places where liquid-like molecular mobility briefly existed during the warmest period. In other areas, the ice contracts into a more rigid form, reinforcing the porous matrix that binds dust and ice together. These changes reinforce the nucleus's structural stability as it adapts to the cold conditions of the outer solar system. The fractures created during active outgassing now stabilize. Without the pressure of sublimating ices pushing outward from within, the cracks remain frozen in place. Their shapes reflect the stresses of the earlier energetic phase, but no longer widen or shift as the internal pressure decreases. These frozen fractures will remain dormant until the comet's next inward passage, when warming will cause them to open again or create new pathways for gas to escape. As the comet moves farther outward, the space around it becomes less influenced by the solar wind. The density of charged particles decreases, and the interactions that once shaped the ion tail diminish completely. The last traces of ionized material disperse into the surrounding environment, leaving no visible sign of the strong activity that once characterized Leonard near the Sun. The dust particles that were carried outward earlier in the orbit continue to drift along the trajectory. Some remain in the broad dust trail that stretches behind the comet, while others disperse further as radiation pressure gradually pushes them into new paths. The comet itself releases no new dust at this stage, marking the complete cessation of tail formation. The coma, once a large and bright cloud enveloping the nucleus, now contracts into invisibility. The remaining gas molecules escape into space as the sublimation slows to a negligible level. Without new gas entering the coma, it cannot maintain its structure. The final molecules drift away until only the bare nucleus remains surrounded by the vacuum of distant space. The surface features that form during the active phase cool and settle. Pits created by collapsing cavities freeze into long-lasting depressions. Slopes shaped by dust movement become stable as grains lock into place under the low temperatures. Some surfaces appear smoother where dust settled evenly, while others remain rugged, reflecting regions where sublimation removed material faster than dust could resettle. These features become part of the long-term record preserved across future orbital cycles. As Leonard continues toward the farthest point of its orbit, the gravitational influence of the Sun becomes weaker and the comet's speed decreases. This slowing reflects the conservation of energy that governs all orbital motion. The comet gradually loses the momentum gained during its descent toward perihelion trading speed for distance as it climbs outward through the solar system. At this stage, the nucleus behaves much as it did before the inward passage began. The dust layer insulates the remaining ices. The internal structure remains frozen and stable. Outgassing falls to undetectable levels, removing the forces that once altered the rotation slightly. The rotation period stabilizes, reflecting the state determined by the internal and external changes of the perihelion passage. The faint sunlight reaching the nucleus no longer alters its structure or drives any detectable activity. Instead, the sunlight serves only to illuminate the surface faintly. Shadows across ridges and depressions shift slowly as the comet rotates, revealing a landscape marked by the processes that unfolded near the Sun. In the deeper layers of the nucleus, the cold temperatures arrest molecular mobility completely. The ices and dust grains lock into place, preserving the chemical and structural composition that has existed since the comet formed billions of years ago. The deeper interior remains insulated from external changes, maintaining the record of the early solar system in its frozen structure. Leonard's outward journey now enters a long phase dominated by stability. The nucleus moves through regions where temperatures remain too low to support any further sublimation. The dust layer continues to protect the ices from the faint sunlight. The fractures and cavities remain unchanged. The surface gradually loses the last remnants of warmth, absorbed during perihelion, settling fully into the cold equilibrium of distant space. As the comet approaches the farthest point in its orbit, the environment becomes nearly indistinguishable from the conditions that prevailed in the distant past, before gravity guided it inward. The dust settles into stillness. The ice remains frozen throughout. The nucleus follows its path at a steady pace, shaped only by the gravitational influence of the Sun, acting across great distances. This outward region marks the end of the active phase and the beginning of the long period of dormancy. Leonard continues along its trajectory, carrying with it the structural changes created during its passage through the inner solar system. These features will persist until the comet once again approaches regions where sunlight grows strong enough to warm the dust and ice. When that time comes, the processes of sublimation, outgassing, coma formation, and tail development will begin anew, repeating the cycle that has shaped comets for billions of years. For now, the comet moves quietly into the far reaches of its orbit, its surface frozen, its activity stilled, and its long journey toward the outer solar system continuing without disturbance as it prepares for the long interval before its next return toward the Sun. Comet Leonard moves through the distant region of its outbound path where the sunlight reaches it as a faint and softened glow, leaving the nucleus in a state shaped by deep cold and long intervals of stillness. The dust that settled across its surface after the period of activity now forms a stable covering that shields the remaining ices from further change. Beneath this layer, the deeper structure cools until the temperatures match those of the far outer solar system, allowing the volatile materials to remain frozen in place. The fractures created during the active phase no longer widen or shift. They remain locked within the rigid ice preserved until the comet encounters warmer regions again during a future inward passage. The pockets of gas that once expanded beneath the surface have refrozen entirely, leaving the interior in a stable configuration that no longer produces pressure. As Leonard continues outward, the last traces of the coma disappear, leaving the nucleus alone against the dark background of space. The dust and ion tails that once extended behind the comet have dispersed into the broader environment, carried by radiation pressure and the solar wind until they blend into the surrounding region. No new material flows outward from the nucleus. The surface remains unchanged, except for the slow settling of dust grains as the comet rotates steadily. The outward motion carries Leonard into a region where the Sun becomes only a distant point of light. The gravitational influence of the Sun still guides the orbit, but the warmth and radiation that once shaped the comet's appearance now exert little effect. The nucleus continues along its path with quiet consistency, following an orbit defined by earlier interactions with gravity and the structure of the solar system. The calm environment around Leonard reflects the stability that characterizes this part of its journey. The absence of activity allows the surface features formed during perihelion to remain fixed. The pit's depressions and redistributed dust that shape the terrain now enter a long period of preservation. These features will remain unchanged until the comet's next inward approach, when sunlight will once again begin to warm the dust and ice. For now, the nucleus travels through a region where time passes without altering its structure. The comet moves with a slow and measured pace, leaving behind the dynamic processes that occurred near the Sun. The dust that once reflected bright sunlight now lies still across the cold surface. The ice remains locked in place, held firm by the low temperatures that define the distant outer solar system. The quiet environment provides a long interval, during which the nucleus remains in a stable and preserved state. Leonard's journey continues along an orbit that will eventually carry it back toward the Sun, but this return lies far in the future. During the long outbound phase, the changes brought by the active period remain frozen in place. The dust layer that blankets the surface protects the volatile materials beneath, while the deep cold ensures that sublimation will not resume until the comet returns to warmer regions. The comet's passage into the distant reaches marks the conclusion of the current cycle of activity and the beginning of a long period of rest defined by stillness, cold, and the slow motion of the orbit.